Okay, let's roll up our sleeves and apply our newfound knowledge about bilinear forms to higher differentials, so to second differentials of functions. Let us sum up what we already know and what we already knew basically before, but now rephrase this in terms of bilinear forms. Corollary 1266. So if n is an n, U is an open subset of Rn, f from U to R is twice continuously differentiable. Then for each A in U, the second differential and just to recall, this is now mapped D to F in the point A from Rn times Rn to R. Let me just write this down once explicitly again. D2Fa of Vw is the directional derivative dv, then dw of f in the point A, where I'm again using the convention that derivation by the zero vector is just zero. Okay, this map here is a symmetric bilinear form. Okay, now we'll not write down a proof because we've seen already everything that we need to see. By construction, it was bilinear. This is what we've already seen, and the symmetry property just means that here we can interchange the order of directional derivatives. And this was a corollary, that was corollary 1245. There we've seen that the order can be exchanged. So this in our new terminology, this means that this bilinear form is symmetric. Okay, so we can use what we know about symmetric bilinear forms, what we've just learned, and we want to make use of this to then discuss local extrema and their properties. Before, one more bit of terminology, and this is something we've actually already seen, but I haven't given it a name by that time. So in the same setting, basically, so n and n, U subset of Rn open, f from U to R, but this time we only assume that f is partially differentiable. For this definition, that's enough. Then a point A in U is called a critical point of f if the gradient vanishes in that point. So if the gradient of f in A is 0. And we have seen that if we have a local extremum in some open set, then the point where it takes this local extremum must be a critical point. This is what we've already shown. Okay, now, Theorem 1268, or one more bit. The set of all critical points is denoted by crit f. So this is, this notation is I think everyone uses a different notation, but this is my version. Crit f is the set of all A in U in which the gradient vanishes. Okay, now Theorem 1268. So n and n, U subset Rn open, and f from U to R is again twice continuously differentiable. And that A be a critical point of f. Then, now, and we will now see that as in the single variable case, we can use the second derivative to determine if it's a maximum, minimum, or neither. And it turns out here, and this is really a beautiful thing, that before we had, so in the single variable setting, that the value of the derivative and that second derivative in that point is positive or negative, that this has a straightforward generalization by just using the definiteness properties that we've seen in the previous section. And this is a very beautiful theorem in my opinion. Namely, first of all, if d2f in A, so the bilinear form d2f in point A is positive definite, then f has a minimum. Local minimum. A local minimum in A. Again, this only is a local statement, so we cannot say much about global maxima and minima. This I will tell you something about in the end of this subsection. B, in the same way, if d2fa is negative definite, then f has a local maximum. In A. And finally, there's a third case, which doesn't appear in the single variable setting because this cannot appear basically. We shall see later why. If d2fa is indefinite, then f has neither a local maximum, nor a local minimum. So in this case, we don't have a local extremum, local minimum in A. So this is what we can tell from the second derivative. So it's the second differential instead of the second derivative here. And so replacing the positivity and negativity of the value of the derivative by just this positive and negative definiteness. Really beautiful result in my opinion. Okay, so let's prove this. And as we did in the single variable case, there we derived the corresponding statement from Taylor's theorem. And we will do exactly the same thing. We will use Taylor's theorem to derive the corresponding result. So, in the following way. First of all, we take a look at Taylor's formula, and we only take a look at the second Taylor polynomial. Namely, if we have a critical point, let A be a critical point of f, so the gradient is vanishing. This is, by definition here, the same as saying that the first derivative as a map is vanishing. So the part of the component of the Taylor polynomials which involves the first derivative is already 0. This is what we already know. So by the piano form of Taylor's theorem, this was theorem 1254, we know that f of a plus h, and now let's write down the second Taylor polynomial. So we start with f of a plus something depending on the first derivative, which is 0. So this doesn't occur here, and then we have the part of the second derivative, 1 over 2 factorial, which is just 1 over 2. And then we get d2f in the point A evaluated in h plus some map phi of h, where phi from u prime to r. I'm not writing down the same thing again, but this is so. Yeah, the phi has u prime here is a nice neighborhood of 0. This is all we need. Phi from u prime to r satisfies the limit as h goes to 0 of phi of h divided by the norm of h squared is 0. Okay. So we want to show now in the first case, so in part A, that if we have a positive definite form here, then we get that this must be the local minimum. So this means if h is kind of walking around in the neighborhood of of 0, then this term here must be non-negative, because then, and also this part must. So everything that's remaining here, this part here must be bigger than or equal to 0, because this then means that f of a plus h is bigger than or equal to f of a. So for this, we need to apply this positive definiteness and the properties of phi, and this is a slight little computation. This so far was true in all cases. So now let's consider case A. First of all, we define a certain set, namely S, which is defined as the set of all x in Rn, which have norm 1. It's the unit sphere, the boundary of the unit ball in Rn. So we have probably seen before, I don't remember precisely, but you can easily see that this has an advantage over Rn, over taking all of Rn, namely this is compact. You can easily see S is bounded, this is obvious, and you can also easily see that it's closed, for example with the sequence condition. If you have a sequence whose norm is 1, which converges, whereby the norm of every element is 1, then the limit will also have norm 1, which follows from the continuity of the norm. Since B is bounded and closed, S is compact by Heine-Borel. So Heine-Borel S is compact. So by assumption, and here we use the property that F is twice continuously differentiable, the following map S from S to R, which just takes G of some element V of this unit sphere, shall be the second differential of F in A of V, comma V. If we boil this down and compute this in terms of partial derivatives, there's only second order partial derivatives involved, and by assumption they are continuous. And from this you can see, when you write this really in terms of the partial derivatives, this map is continuous. But we've seen that a continuous function on a compact subset of a metric space always admits a maximum and minimum. This was, have I written this down? I haven't written down the precise theorem, but F has, or attains, G, not F, G attains, and we only need the minimum, M in R. So little m is called the minimum. So that's the name we use for this. Now, first of all, since D2FA is positive definite by assumption, this is a part where we really insert, so I mean this is just some bilinear form, but we insert twice the same vector, and if it's positive definite, this is positive for all non-vanishing vectors. In particular, this must be, this takes only positive values, so G of V is positive for all V in S, and in particular the minimum must then be positive, because the minimum is just really one of these values, and if they are all positive, this means M must be positive as well. Okay, so it has a positive number as a minimum, and now we do a little computation using bilinearity basically. So for some H in Rn, which is non-zero, we now compute the following, and we will now use this property to get a nice estimate for the second differential of any vector, not just vectors in S. I mean, here we insert some H in Rn, so some vector H, and here we insert only vectors from the unit sphere. That's the difference here, but we can reduce basically everything to this unit sphere, to this map, to the set S. Namely, we compute the following: D2F in A of H, H. We can now write this as scalar multiples of elements of S, namely by just putting D2FA. This is the same as the norm of H times 1 over the norm of H, and the same in the second factor. This looks pretty pointless, I must admit, but we will see why we use this. Namely, if we take a look at the norm of this here, the norm of this, by the properties of the norm, this would be norm of H divided by norm of H, which is 1. So this here is an element of S, and this here is an element of S. And since it's bilinear, this second differential, we can just take these two constants there and factorize them out. So we do this once, we do this twice, and then we end up with the norm of H squared times dfa of, I can abbreviate this. So dv, I don't know, maybe do this in detail. This is not that simple. So we have twice this term here included. And since this is an element of S, this is by definition just the norm of H squared times G of 1 over the norm of H times H. Okay, and this must be something, but we know that this is, M is the minimum of G, so this is bigger than or equal to M times the norm of H squared. So this was true for all non-zero vectors, but this easily implies that, so let's summarize this, d2fa of hh is bigger than or equal to m times the norm of h squared for all h in Rn. Okay, and this is easy to see because the only thing that we haven't checked is the zero vector, but if we insert 0 there, we have 0 on both sides, so this holds true as well. So by this we can estimate this second differential from below, which is a useful thing. And now we just need to make things work here and see that phi doesn't, so this, I mean by this we see that this expression here is bounded from below by some positive thing here. So all that's left to see is to see that phi, which is this rubbish function, this must be so small that this doesn't make this here negative. So we just have to see that this is small enough. And this is an easy line of argument just by this limiting property here. So since, let me call this small equation star, namely by star, we know that if we are close enough to 0, we know that there exists some small r in 0 with br of 0 in u prime. So if we just are close enough to 0, then we can always expect, since this holds, this goes faster to 0 than any than the square here. This means that the absolute value of phi of h is smaller than or equal to 1/4 m times h squared, norm of h squared. Namely, if we divide this by that expression, this is smaller than or equal to 1/4 of m, so some constant value. But we know that if we divide this by here, that the whole expression, the fraction, then must go to 0. So so we know that this is indeed smaller at some point. So this gets smaller than every positive value at some point. Now, if we just put together this and this, then we have already done it. But here, for this point, I need to erase, and then we'll conclude the proof of that part. This was the equation we had derived from Taylor's theorem. So if we now insert the estimates that we had, we can see that this is bigger than or equal to f of a plus, and here we had 1/2, and now we have m times the norm of h squared, where m was this minimum of this function g again. And here we had seen that the absolute value of this is bounded from 1/4, or we had assumed that for sufficiently close h sufficiently close to 0, we had seen that the absolute value of this was bounded from above by 1/4 of m, the norm of h squared, which means that if we estimate the pure term, this is bigger than or equal to minus 1/4 m norm of h squared. And here we of course see that this is the same as f of a plus 1/4 m h norm of h squared, and we had seen that the minimum here must be positive. This is not negative anyway, so this here is all bigger than or equal to f of a, and this goes for all h in br0 for some small r bigger than 0, whose value is not important, because all we need to know is that this inequality holds for some open neighborhood of our point A. So this means f has a local maximum in A, which we wanted to show. I find this proof very beautiful, I hope so do you. Okay, part B, the negative definite case, basically it's almost the same. And this time we consider again this function g, but this time we need the maximum instead of the minimum, and need to kind of consider some inequalities going in the opposite direction. So let me just write here analogously. So this is basically the same thing with slightly different arguments, but anyway. Okay, part C is more interesting. So if the second differential is indefinite, then we have neither a minimum nor a maximum. And this is an interesting thing. So, namely, we do the following. We take two vectors, v1, v2, in Rn, such that, and this is now the assumption, it's indefinite, the d2f in A of v1 is positive, while d2f in A of v2 is negative. Okay, this is what we assume, that such vectors exist. Now, if we got such vectors, we play along with them. Namely, we do the following, that epsilon bigger than 0 be so small that a plus t times v1 or v2, so let me put here vi, is still in u for all t in minus epsilon epsilon and I in 1, 2. Okay, such epsilon we can find since U is an open map, so it's a neighborhood of A, and then we always can find such an epsilon. Okay, if this holds for these two vectors, then let gamma I be the curve from minus epsilon epsilon to U, which we get by gamma I of t is A plus t times Vi, and we define Gi from minus epsilon epsilon to R by just taking Gi as the composition of F with gamma I for I in 1, 2. So we take a small segment, which is kind of, a small line segment on the line spanned by this vector Vi through the point A, and just take the value of f on this. And we want to see basically, if we take these as real functions, one of them has a minimum and one of them, local minimum, and one of them has a local maximum in 0, which corresponds to the point A. So if in one direction we get smaller values, in the other direction we get bigger values, this can't happen. So this means we can't have a local maximum of f in general. Okay, so f is twice differentiable. These gamma i's was just a plus some constant t times a vector. This is differentiable as often as you want. So we get that g1 and g2 are twice differentiable. Satisfy, first of all, g1 of 0 is the same as g2 of 0 is the same as a, and we can compute the derivatives of them in the same way. So gi prime of t, and this is now by this result about compositions of curves with functions here. There we had the formula for the derivatives, and this was just df in the point gamma I of t of gamma I prime of t. So this is by, in our new notation, basically the inner product with the gradient at gamma I of t with the derivative, which is just Vi. And if we write this down, these V1 and V2 that I'm choosing, I want to label the entries as V11, V12, and so on, to V1n for the first vector, and V2 is then named V21, V22, to V2n. Okay, now this is the same as that, and so if we want to have this more explicitly, we could use this formula in terms of partial derivatives. So this is the same as the sum, I can use I here now, j from 1 to n of partial jf in the point gamma I of t times the jth component of Vi, so Vij. Okay, but this means, so since we are, when we study the point 0, this means that gi prime of 0, this is also for I in 1, 2, so for both cases this holds. This means the derivative in 0 is, by that formula, the same as the gradient in gamma I of 0, which is nothing but a with Vi, but the assumption was a is a critical point, so this is 0. Okay. So this means we have the sufficient criterion here for a local extremum for these two functions g1 and g2. Okay, to check if they are really local extrema, we can discuss the second derivatives, namely, gi double prime of t. Let's compute this. And again, this here, if we use this form here, this is basically again the composition of a curve and a function here, or the sum of n such terms. This means that we can just write this in a nicer way as the sum from j equals 1 to n of the derivative of djf composed with gamma I of t this is some real function, times Vij. And this is by the same formula as before, the sum over j equals 1 to n, djf in the point gamma I of t applied to gamma I prime of t, which is Vi, times Vij. And if we just write this again in terms of partial derivatives, this is the same as the sum j from 1 to n, sum k from 1 to n, dk dj, f in the point gamma I of t, multiplied with Vij, Vik. But if we take a closer look at this expression, this is precisely the second differential. This is what we've computed in this theorem definition 1248, where I introduced the higher differentials. So this is exactly the same as d2f, d2f in the point gamma I of t, evaluated on, there's, yes, Vi, sorry, yeah. Okay, so this is what we've computed here now, but this particularly means, so we wanted to discuss the term t equals 0. This means that g1 double prime in 0 is d2f in the point A, which is gamma 1 of 0, of v1, but we've just constructed or chosen these vectors such that this is positive. So this is positive, and in the same way we get that g2 prime of t is d2fa of v2, which is negative. So this means 0 is a local minimum point for g1 and a local maximum point for g2. So we have two curves going to the same point, and one of them, so it's, maybe it's hard to draw, I will show you later an example, but here you have basically two directions going to the point. In the one direction, the values are getting bigger. In the other direction, they are getting smaller. So it cannot be a maximum or a minimum. So it follows, and I will spare you the details. This is contained in the lecture notes, the rest. F does not have a local extremum in A. So this shows that. So we can really use the second differential to show that something has, at some point is a local maximum or a minimum. But of course, the task is now to show that the bilinear form is positive or negative definite. But the good news is this is a bilinear form on Rn, so by what we've learned in the previous subsection, we can just represent this by a matrix. And if you take a closer look at this, this matrix is not that complicated after all, and this is something that is indeed computable. So this is something where we can really use our linear algebra knowledge then to tell if we have a local minimum or a local maximum in the following way. So we have n in n, u in Rn open, f from u to r is twice continuously differentiable. And we take a point A in U. Then we know that, so first of all, we know that we have a matrix which, you also say represents this bilinear form, namely D2A evaluated, D2F in the point A of VW. This is now the same as the inner product of V with the matrix times W, and this matrix is called HF of A. Okay, we know that such a matrix exists. And we can write down this matrix explicitly. So this is a quadratic, so an n by n matrix with real entries. Now I don't have that much space. That step was not very smart of me. Anyway, you can show that hf of a, the entries of this, the aij entry is di dj f in A. So if you write this as a matrix, we have d1, d1, f in A, d1, d2, f in A, and so on to d1, dn, f in A. And we do the same in every line, every row until we get dn, d1, f of A, dn, d2, f of A, dn, dn, f in A. Sorry, almost readable. So we just put all the second order partial derivative into one big matrix, and these are really numbers. This is something we can compute. This is a pile of numbers. So just put all the partial derivatives in there. And how do we see this? And one more bit. Let me use this blank space here. So first of all, so this matrix which contains all these second order partial derivatives has a name. HF or A is called the, so this was the theorem part. Here it's called the Hessian matrix of F in A, or simply Hessian of F in A. Now, this name might sound a bit weird. Sorry. This comes from the name of Otto Hesse. There was a German mathematician who invented this. And so from Hesse, there was this adjective Hessian, which is a bit strange, but yeah, just don't get confused by this. This is called the Hessian matrix of F and A, or the Hessian. And something where this fits in nicely with what we've seen before, we've seen Schwarz's theorem, which says that the order of partial derivation doesn't matter. This means that this matrix here, so for example here in the top right corner we have d1 dn f of a, here we have dn d1. So these two must coincide, and if we look at this at every entry, this shows that this matrix is symmetric. We could derive from Schwarz's theorem, but we already knew it before basically because we knew that this is a symmetric bilinear form, and so we've learned in the previous subsection that then the matrix must be symmetric here. Okay. Let me lose a few words on the proof after I erased, basically. I need some more space for this, and yeah, then we'll go on. The good news is there is not much to prove because we can just use the corresponding result for bilinear forms. Namely, it follows from corollary 1261, which describe point C, which described the entries of the matrix representing a bilinear form, that this matrix, so H f of A, the entries of this must be D to F with EI, EJ inserted. So we take a basis and insert the basis vectors there, and the matrix is representing this by respect to the canonical basis here. So we just insert the canonical basis vectors here at that point, and just by definition, this is the same as the matrix Di, Dj of F in A. This is A. This is precisely the way that this is defined. So this already shows the claim, so there's nothing left to prove. Okay, so this means we can use the definiteness properties then for Hessians. So let's just rephrase this one theorem that I had before about local extrema. So let n in n U in Rn be open, F from U to R twice continuously differentiable, and a point in U. So then we can just rephrase everything by the definiteness of the Hessian. I mean, this is what we've already seen. So A and U be a critical point, so with vanishing gradient of F in that point. So just these 3 points. Let me take a shortcut again. Yes, hello, support? It's you. Yeah, could you help me again? Could you just fill in the details here? Yeah, okay, guys, very funny, but please, could you just help me out here again? Wonderful, thanks again. Okay, so here we've got the details. So this is basically just rephrasing everything with matrices. So if the matrix If the Hessian matrix in A is positive definite, then we have a local minimum. If the Hessian matrix is negative definite, we have a local maximum. And if it's indefinite, we have neither of the two. Okay, so this is something we can check. I mean, these terms, as I said, depend only on the eigenvalues of the Hessian. And this is, again, we can compute the Hessian at a point as a matrix with really numbers as entries and compute their eigenvalues by the methods from linear algebra that we learned. And in this way, we can then really compute if something is, if something is a local maximum, a local minimum, or not, or neither of the two. Okay. As an example, I want to show you several functions and see things that might happen there. And for the first bit, I want to switch to GeoGebra again and switch to a screencast video that I'm including now. Okay, we're back in GeoGebra. This is our three-dimensional coordinate system here. As before, as in the previous examples, the red axis is the x-axis, the green axis is the y-axis, and so these are the coordinates in R2. And for a function in R2, the blue axis displays the value, which would be the z-axis here in R3. So this light gray plane here, this is the xy plane, this is the domain of our functions. Okay, I've prepared the three equations, as you can see here. So f1, f2, f3 as in the example. So let's first take a look at f1. I think we had this already in the demonstration video for GeoGebra. This is what this looks like. This is what we call a paraboloid. And you can see here, like if you imagine that one of the coordinates is 0, so if we fix y at 0 or x at 0, we get just the standard parabola, which is just like, for example, if we display it like this, almost, okay, this would be like a projection onto the y coordinates. So if x is equal to 0, you can see the idea. So we would just get a parabola here over that green line, and in the same way over the red line, if we keep take a look what happens if y vanishes. This also looks like a nice parabola, so the standard parabola x squared over this axis. And in the same way, this is kind of, if you would draw any line through this origin, you would get a parabola over that line. And these black lines on the graph that indicate kind of what happens if we fix the x values here to be 1, 2, and so on. And in the same way over the green axis, we have these black lines here which indicate what happens if we fix the y value at 1 or 2 or whatever. So with regards to our problem here, we see that 0 is a point where the gradient vanishes. I've mentioned the gradient as an example in the lecture where it's just pointing away from the origin, and the length of the gradient increases the further we get away from the origin. But if we take a look here, so the gradient in the origin is 0. This is the only critical point there. And here we see really it's a local minimum, and it's not only a local minimum, it's really the minimum of the function, because it's increasing and increasing and increasing. But at this point you can see kind of, everything is like in every direction it looks like a parabola which has the minimum here in 0. Okay, this is the simplest example, and here we've seen also by the taking a look at the Hessian and so on that this is really a minimum, so this fits with our observations. Now if we take a look at the function, if we remove this one and display the function f2, which is minus x squared minus y squared, we just get the same upside down, right? So at this time we've got, like if we fix one of the coordinates, we would get just minus x squared or minus y squared in this example here. Over the coordinate axis and in every direction. So if I kind of rotate this always looks like a nice parabola in every direction. So the, again, this behaves in the same way, but this time we have a maximum here. We have seen that here in this case the Hessian is indeed negative definite, and so here this fits with our observation. This is really a strict, this is also not a local maximum, but the maximum of the function that's taken there. So the maximum is 0, which you can easily compute. So this would correspond to just going the other way around. Now the most interesting case is for the third case, which was the case of an indefinite Hessian, where we saw that it's neither a maximum nor a minimum. So what's the difference to the other cases? Let's remove this one, and now let's display the graph of this function x squared minus y squared. Okay, this looks wild. This is what we call a saddle point also. I haven't used this term so far. And the best way to understand this is the following. Assume we fix y to be 0. So let's take again this projection on the xz plane. So then we see, whoops, almost like this. In this case, we would have just f of f3 of x0 is just x squared. So over the line where y is 0, we just get the parabola x squared, right? Which is kind of the boundary line of this curve here. So this is what we see there. Now, if we go the other way, if we fix x and just take y as a variable, we see that then it's getting minus y squared. So if we would do the same with the other axis, I hope this is visible here. Yes, wonderful. Yeah, almost like this. We would get the boundary of this graph here, so which is minus y squared. So in this case, in the one coordinate, it would have a maximum, because in the one coordinate it looks like this, but in the other coordinate axis it looks like this, so we have a minimum there. So we have it one direction, and yeah, if we would restrict the function to lines through the origin, we can find a direction where it's a minimum, we can find a direction where it's a maximum, and this is exactly how we proved that this is then neither a minimum or a maximum. We have picked two directions, and this would be the kind of, yeah, the eigenvectors of the Hessian in this case that correspond to a positive and a negative eigenvalue there. So we can see there are two such directions, and this is the general phenomenon. So if we would just kind of modify things a little, the principle would stay the same. So we would get this funny looking graph, and you can see also, like in the one direction, like in the, always if you take a black line which is kind of fixing the x coordinate and just taking y, which would be one of these lines here, they go kind of like parabolas here, up and down again. And in the same way, if we would fix the green variable here, so the y variable in this direction, we always get parabolas looking the other way. And this is what you also call a saddle point if something has this particular shape. And you can, if we just modify our function slightly, let's say we add, I don't know, xy, for example. So you see we've basically got the same situation, only if we take a look from the top, we see that our axes are slightly shifting. So, whoops, this is a slight disturbance. So it's no longer if we look over the axis and get the parabolas here, but we just need to take a slightly different, we have slightly different eigenvectors of the Hessian there. So we have the direction here is changing a bit. Let's maybe increase this by, I don't know. Let's say we disturb this pretty heavily. Let's add 10. Then you see basically it just also behaves slightly differently. So the slope is much bigger. But in the same way, we can then find one direction in which it's a parabola in the one direction. And if we turn it around, there will be a direction where it's going downwards. And this general phenomenon is what happens with an indefinite matrix. With these impressions, I'm giving back to the seminar room. Okay, I hope this was illuminating. For the second part, I want to show you something different. Namely, if the Hessian HF of A has none of the definiteness properties of the above definiteness properties, then it's kind of impossible to say what happens. So I just write anything can happen. And for this, I consider a concrete example. Namely, we consider three functions, f1, f2, f3, similar as in the first part of the example, from R2 to R, where f1 of xy is, and they now look very similar to the functions from above, x squared plus y to the 4. f2 of xy is x squared minus y over 4, and f3 of xy is x squared plus y to the power of 3. Okay, so these have many things in common, these functions. Namely, we can see that for all of them, we have the same values of f, of the gradient, and of the Hessian. Namely, if we compute, so first of all, fi of 0, 0 is 0 for all of them, obviously. And if we take a look at the gradient, we see that this is, if we derive this, we always get powers of x and y, and there it's easy to see that the gradient is also vanishing. So gradient of fi is also 0, 0. There's also 0 in the point 0, 0 in the origin, so we have a critical point there. And we can see that the Hessian hfi of a, and this is because we have these higher powers in there, you can compute, the mixed derivatives. So if we first derive by x and then by y or something, then they will obviously vanish. If we derive twice by y, we will always have something, some power of y left, because here the lowest index is 3, and so the second derive this twice, we will still have a y left, and the other two we have a y squared left, so this will also be 0, and only here we will have 2, because there's always this x squared everywhere. So this holds for all I from 1 to 3. But the behavior of the functions at that point is completely different. They have, two of them, no, one of them has a maximum in there, a minimum in there, one of them, and the two of them don't. But there's also different behavior for these two, and since I want to show you this again in detail, let me switch again to GeoGebra. Okay, let's take a look at this example, and I've again prepared the three functions that we're studying here, and we will see that behavior is very similar to what we've seen before. So these are functions for which the value of the functions is the same, the gradient is the same, and the Hessian is the same in the origin. So let's take a look at the behavior. Here we can see for x2 plus y squared, it's the same principle like with x squared plus y squared with the two parabolas, only this time in the y coordinate. So if we fix if we fix x to be 0, which we can look at this from the side, this is no longer a parabola, but this is x to the 4. So this is the graph of x to the 4 is very visible here, which is kind of increasing much faster here and going faster to 0 if we're close to the origin. And in the other direction, it remains the parabola. And so this kind of interpolates between these two curves. So we see it's no longer so nice rotationally symmetric, but for our purposes, we can still see it's an absolute minimum of this function. So it's really not, it's a local minimum, but it's also just a minimum of the function itself. Now, if we take the second example, x squared minus y to the 4, then we get again such a saddle point, only this time same effect. In the one direction here, we've still got our nice parabola if we fix the y coordinate equal to 0, because we then get y squared, x squared, but in the other coordinate we have y to the 4. So we just see that in this coordinate we have this y to the 4, whoops, the graph popping up there. So it's basically some distorted saddle in that sense. So it's not behaving that symmetrically. So in the y direction is going down much faster than before, but it's still a saddle point. So the principle is still the same. We have a direction in which the function has a minimum and one direction in which the function has a maximum here. So the same principle we used in the proof is applicable here. And again, I could disturb this function a bit, but here we still see that we have the saddle point phenomenon. So another interesting case is the third example. There it's also neither a maximum nor a minimum, but here it's a different way. Here the matrix is also not indefinite. This is a case, let's maybe take a look at this first. So if we take the y variable to be 0, now it's a bit harder to see. We get this black line here. This is the part of the graph which lies over the x-axis. This is again x squared. But as you can tell, if x is equal to 0, then we get y to the 3. And if we take a look at this from the side, this is the graph of x to the 3, or here y to the 3. So we see in this direction we've got this graph here. So still, it's not a minimum or a maximum in this case. We have bigger and slower values always near 0. There's kind of a plateau here. But it's a difference to the saddle point phenomenon, because here we see in the one direction, so over the x-axis, this is a minimum there. But in the y direction, it is neither, because we have this passing through. So there's no concrete direction for which this point here is a maximum. So also this might occur. And this is an example where the Hessian is not indefinite and also not positive definite. In fact, this is something called positive semi-definite, but this is also a case which is sometimes called degenerate if these phenomena happen, so that we cannot decompose kind of the domain into spaces in which it's a maximum or a minimum. So here we've got this case where this is kind of not our methods there would not be applicable to this function directly, because the Hessian simply doesn't have the nice properties. But this is what can happen here as well. Okay, back to the seminar room. Okay, let's do one more explicit example of a slightly more complicated function. Consider f from R2 to R, where f of xy is x squared plus x minus 2 squared plus x y squared. This time I leave this up to you to display this function in GeoGebra, which I cordially invite you to. This is easy to input there, and then you can maybe see what's happening. So let's consider the local extrema of this. So f is a polynomial, and there you can see it's continuously partially differentiable as often as you want. So in particular, it is twice continuously differentiable. And we compute the following. So we compute the partial derivatives, d1fxy, so deriving this by x. For the first summand, we use the chain rule. The exterior derivative is the derivative of the outside function. This is twice times the expression there, so twice x squared plus x minus 2 times the derivative of everything inside the parentheses, which is 2x plus 1. And here this derived is just y squared. And d2f of x, y is, so just deriving this by y, this is of course, this is just 0. And if we derive this, we get 2xy. So let's learn about this explicitly. So this is the partial derivatives. So the critical points, of f are given by the following equations. So we know that the gradient is 0, so these two must be 0. So this means d1f xy is 0 and d2f xy is 0, so they both have to hold simultaneously. This is the same, so by this computation, as 2x squared plus x minus 2. No, wait, what did, yeah, right, 2 times 2x plus 1 plus y squared must be equal to 0, and then 2xy must be equal to 0. So let me call them equation 1 and equation 2. So yeah, the second one is of course easier. So by 2, this means that this holds if and only if either x is 0 or y is 0. One of them must be 0. Now, if x is 0, then what do we get in the first equation? So here we get 2, and here we get 0 plus 0 minus 2, and here we get 0 plus 1. So 2 times minus 2 times 1, which is minus 4 plus y squared is equal to 0. And this is, of course, very simple to see the solutions. This is the case if and only if y is minus 2 or y is 2. Okay, on the other hand, if y is 0, then 1 becomes, so just, I mean, this expression just vanishes. So twice this must be 0, and of course the 2 doesn't matter. So we just need x squared plus x minus 2 times 2x plus 1 is 0. This is of course equivalent to either the product is 0 if and only if one of the factors is 0. So x squared plus x minus 2 is 0. Or x, and you can just easily derive from this that x is minus 1 over 2 is the solution of that equal to 0. And for the first equation, this is just solving a quadratic equation. That's very basic, and I don't want to go into detail on this. This has just the solutions x equal to 1 and x equal to minus 2. So this happens. So let me just summarize this before erasing and going on. This means we have 5 critical points. So the first two are here with x equal to 0, then y is 2 or minus 2, so we get 0, minus 2, and 0, 2. And finally, if y is 0, we get 3 solutions, so either x is 1, which would get 1, 0, or x is minus 2, which is, so here, minus 2, 0, or x is minus 1 over 2, which gives minus 1 over 2, 0. Okay, so at this point, what we need to do is to compute the Hessian. So first the general form and an arbitrary point, and just insert these points, take a look at the different matrices, and take a look at their properties. And this is what I shall do after erasing. Okay, we still need to compute the Hessian matrix. So let's do first the general form, hf in the point xy. So this is only 2 by 2 now, so we have only a function on R2, so it's just d1 f of xy, d1 d2 of f of xy, d2 d1 of f of xy, and finally d2 d2 f of xy. Okay, now I just want to spare you the details here, but this you can, again, just by taking partial derivatives from the partial derivatives that we already had, so deriving them again, we get that this matrix is given by 12x squared plus 12x minus 6, if we derive that expression again by x and kind of compute this as a polynomial. The other ones are simpler. We had 2xy as the second derivative, so deriving this by x, we just get 2y. And this here, since the matrix must be symmetric, must be the same as this, so we don't even have to think about this. And again, deriving this 2xy by y, we get 2x. Okay, what does this mean? This means for our critical points the following. The Hessian in the point 0, 2. So what does this look like? I mean, this is 0. This is 4, and here you get minus 6, because there it's 0 and you have minus 6. HF in the point 0, minus 2, it's almost the same, but the only difference is that there's a different sign over there. Sorry, not over there, or there, in these two entries. So we get minus 6, minus 4, 0. And for the other three, we get the following. HF of 1, 0 is, and so we already see that this entry is gone and this entry is gone. And so here we have 2, and finally there we have 12 plus 12 minus 6, so 24 minus 6, which gives 18. Then we have minus 2, 0 as a point, and again we have 0, 0 here. So there we have minus 4, and here it's, wait, what did I just compute? Yes. This is 18 as well, I think. This is 84 minus 24 is 24 minus 6 is 18. Yeah, sorry about that. Okay. And finally, we have one more point, HF of minus 1 over 2, 0. There we just get, let me abbreviate, minus 9, 0, 0, minus 1. Okay, and from this we can now check what properties these Hessians have, or what properties these points have. So what about definiteness? Here it's easy to see, because if the matrix is diagonal, we can see the eigenvalues. The eigenvalues are just the values on the diagonal. So here we can see we have two positive numbers on the diagonals. So this is positive definite. Here we see that we have a positive and a negative eigenvalue in there. So this is indefinite. And here we see it's negative definite, because we have two negative eigenvalues in there. Okay, here we need to think a little bit more, but I had this criterion for 2 by 2 matrix that the determinant is important here. Here we see that the determinant of H2 of HF in 0, 2, so this is minus 6 times 0, minus 4 times 4, so minus 16, which is a negative number, and this implies it's indefinite. This was the corollary the last corollary in the subsection about bilinear forms. And the same here. This is minus 6 times 0, minus 4 times minus 4, so 3 times minus. So here as well, the determinant of HF in 0, minus 2 is also minus 16, which is negative. And so this is indefinite. So the indefinite points mean we don't have a local minimum or a local maximum, but the positive and negative see that we have one of each. So F has a local maximum in minus 1, 2 with value, and this is something we can now compute, F of minus 1 over 2, comma 0, and let me abbreviate, this is 25 over 16 if you compute this, and a local minimum in this point here, 1, 0, with value f of 1, 0, and this is something you can easily check. No, sorry, I don't have f on the board anymore. the value was, let me read this off, 0, just 0. And no other local extrema. And that's it. Okay, this is how you can kind of discuss local extrema of a function in that way. Okay, at this point, this was everything you need for the exam. This is now the big cut. Everything that's coming from this point on is no longer relevant for the exam and you won't need it. But I want to slightly go on in this section a bit. So all that's coming is just a bonus and the rest of the video can also be skipped.